Okay, we're back. We're going to do these 5 curve sketching problems, and let's go. Okay, first function, f(x) equals x squared minus 6x plus 12 over x minus 4. This should strike you as extremely familiar because we did problems exactly like this in Precalculus a lot, you know, for 2 weeks or something. Alright, so that's one of the things that maybe makes this topic hard, is that you're expected to draw from that experience and to combine all the old skills you had plus new skills. So what were all the old things that we would do when given a problem like this? Well, we would factor. I guess this factors, or I guess I hope it does. Whoa. Yes, it doesn't factor? Come on. That's really sad. 2 things which multiply to be 12 and add to 6. Yeah, it doesn't factor. That is surprising to me. Okay, well, that means it's just one of those annoying type problems. So, no fear, we now just use the quadratic formula to find the roots of the top, or to see if it has any. So, what's x? It's negative b, so 6b squared minus 4ac. Have I copied this problem down correctly? I have. Okay, so that's, this was unexpected, but okay, whatever. All over 2, but anyway, there are no such, this is just, you know, not gonna happen. Because that's a negative number under the square root. Alright, so that was nice. What did I just learn? I just learned that this function has no roots. That's pretty important. Well, then I have even less work to do because we can just make the sign chart immediately. The sign chart is going to depend only on the denominator because this numerator has a leading coefficient positive, so the end behavior is like this, but it also has no roots, which is to say it's always positive. So if this numerator is always positive, then it can be ignored on the sign chart. And making a sign chart for f now, I see that it changes sign from negative to positive at x equals 4. Also, the domain of this function is going to be everything except 4, of course. And that's because and I guess there's a vertical asymptote at x equals 4. This is all just old stuff. What else did we do back in Precalculus? We recognized that in order to compute the end behavior of this rational function, then we need to do polynomial long division. So let's do that. X squared minus 6x plus 12, and we divide by x minus 4. So that gives us x squared minus 4x. So yeah, cha-cha-cha-cha. And that goes in minus 2 times, so that's minus 2x, that's 8, and this 4. Yeah. So, what does that tell me? It tells me that this function is actually the function x minus 2 plus 4 over x minus 4. So it's actually relatively straightforward rational function. There's a vertical asymptote at x equals 4, there's a slant asymptote at y equals x minus 2. It's all review. And I think I'm going to not have enough board space to do these problems, so let me try to kind of write small now. What will the graph look like? And you might think we're almost done with this problem and we haven't even done any calculus yet, and you would be right. We have a vertical asymptote at x equals 4. We have a slant asymptote y equals x minus 2. Does this function ever cross its slant asymptote? No, because this numerator 4 is never 0, so this is always something. And therefore, there's nothing I can plug into this function that will give me back exactly x minus 2. And therefore, the function's never, for no x value is the output that number minus 2. Okay, and and I can probably plug in 0. If I plug in 0, I get negative 3. So, oh man, we are just basically done with this problem. Because we know down here, the y-intercept is negative 3. We know that there are no roots. We know that it's negative until 4 positive thereafter. and we know that, well, vertical asymptote at x equals 4, and so we are done. Okay, that is exactly what we did in Precalc C, and that's what you were expected to do in Precalc C. But you will recall, hopefully, that when we were doing this, we sort of went out of our way to call this a sketch, not a graph, although that's just my own vocabulary for this, because one of the things that was left unexplored, because we simply didn't know how to do it, was to find where the relative extrema were for this problem. And this caused some of you some stress, I think, because you felt that it was somehow not right to draw this without knowing where the peak was. That seems like an important kind of thing. So I'll put green circles around the fact that we just didn't know what those were, and we didn't try to know. Well, welcome to the exciting world now of calculus, where we can do these things. And so the calculus that we need to do for this problem is really only going to answer that question. That was the only thing we didn't know. Alright, without further ado, let's graph this function, or no, let's do some calculus. So we have to take the derivative of this function, so let's go. I will use the quotient rule. Derivative of the top times the bottom minus the top times the derivative of the bottom, which is 1. Derivative of the top times the bottom minus the top. All over the bottom squared. Alright, so that's a big ugly mess. Let's go. What do we get? 2x squared minus 8x, so minus 14x plus 24 minus x squared plus 6x minus 12. And just continuing to simplify the numerator gives me x squared minus 8x minus 12, plus 12, all over x minus 4 squared. And that does factor as x minus 2, x minus 6 over x minus 4 squared. Okay? Could almost stop there, but no, I shall push on by taking the second derivative. And the second derivative of this function, well, I'm going to use, I suppose it makes sense to use this version, perhaps. So let's go. So it's derivative of the top. So 2x minus 8, derivative of the top, times the bottom, x minus 4 squared, minus the top, times, oh boy, times the derivative of the bottom. And the derivative of the bottom, derivative of something squared is 2 something back inside 1. All over the bottom squared, so that's x minus 4 to the 4th. Okay, so since all I care about is the sign of these two derivatives, then I really just need to simplify this numerator. This doesn't look fun, but okay. Well, let's just go. I can take out an x minus 4, and I can take out a 2. And I can take out a 2. So taking out a 2 out of this 2x minus 8, and an x minus, well, in fact, this is just 2x minus 4. And so I'm left with x minus 4 squared. And then minus all that. So minus x squared plus, well, I'll just write it like this, minus x squared. I'm just doing some advanced factoring. It's not even that advanced. Okay, and continuing to simplify just the numerator because I'm running out of board space. This becomes 2x minus 4 x squared minus 8x plus 16 minus x squared plus 8x minus 12. Oh boy. And this is, oh, everything cancels except the 4. So this becomes 8 over x minus 4. Okay, I'm going like kind of as fast as I can here. And I'm pretty good at algebra. So that becomes 8 over x minus 4 over x minus 4 squared. No, 4th. Meaning that this is really my final answer for the second derivative is that it is 8 over x minus 4 cubed. That's the second derivative. Okay, so I put a box around this second derivative, and I will put a box around this first derivative. And what I have just done is a lot of calculus and a lot of algebra, and I believe all correctly. And now I'm going to make sign charts. And okay, so what is the appropriate sign chart for the first derivative? I always label my sign chart so I don't confuse myself. Well, looking at it here, I can see that the denominator will always be positive. So all that really matters is 2 and 6. So here's 2, here's 6, and it's a quadratic. It looks like this. So it's plus, minus, plus. And that tells me that my function is increasing, then decreasing, then increasing. And directly beneath, I make a sign chart for the second derivative. And I see here that if you cube something, then if you cube something negative, it's negative. If you cube something positive, it's positive. So it matters whether x minus 4 is positive or negative, and it will be positive greater than 4 and negative less than 4. So right here at 4, there's a sign change from negative to positive. And the sign of the second derivative tells me whether a function is concave up or concave down. So the second derivative is negative, this is concave down, and this is concave up. Okay, so all of this calculus reveals the details that I couldn't quite figure out before when I was doing this just using precalculus only. And, well, what details are revealed? There's a relative max at x equals 2. Oh, congratulations! I now know that it's precisely at x equals 2, which is very plausible, where this function has its relative max. If I plug into, do I really have to do this? I get, what do I get? 4 and 12 is 16, minus 12 is 4 on the top, and negative 2 on the bottom, so it's negative 2. So we have a nice, happy little relative max here at 2 comma negative 2. And where else do I have relative extrema? Answer, my first derivative changes sign from negative to positive at x equals 6, which means my function is decreasing up until 6 and increasing thereafter. And so, yeah, relative min at x equals 6. And so now if I plug 6 into this function, eventually I'm going to make mistakes, but anyway, let's see, that's 36 and 12 is 48, minus 36 is 12, over 2 is 6. So at 6 comma 6, boom, there is a relative min. And so my function must look like this. And, well, then out like that. So that the relative min at 6 comma 6. And then all this effort from this point on, it was quite a lot of effort, to come up with a formula for the second derivative. All that did was to confirm for me, with calculus, that indeed my function is concave down to the left of 4, okay, well, duh, and concave up to the right of 4, okay, well, duh. That was very expected, so this confirms that. Okay, so this took, let's do a quick check-in. This took 13, 14 minutes to graph this function that we mostly knew how to graph already from Precalc C, but by adding in new techniques, we can get all the information now that you could possibly want. Okay, I'm gonna erase this, and yeah, these problems, they just take like 15 minutes each or something. That's just a fact. Okay, so 17 down, now 19. 19, x root 4 minus x. Okay. X root 4 minus x. Well, now this is the kind of function that you could probably also wing this. If you were a smart pre-calculus student, you could probably figure this out. But let's not do that. let's just, this time, well, yeah, you have to do everything. So maybe we should start with sort of the precalculus. What's one important thing to note? Well, you can take the square root of anything. You can only take the square root of positive numbers. And so x has to be less than or equal to 4. And so, but I guess anything else is okay. So the domain is everything from negative infinity to negative 4. Stop. Okay, that's important. And what are the roots of this function? 0 and 4. So those are places where this function is 0. And maybe just even right now, we can make a sign chart for this function, or we can do it later. Yeah, we can just do it later. And then, anything else worth mentioning? I don't think so. Odd, even, end behavior. It's going to go off to infinity when x is like negative a million. Well, maybe that's worth mentioning. As x approaches like negative infinity, like if you plug in negative a million in here, then that's 4 minus negative a million. That's a huge positive number that you're taking the square root of, so that's pretty huge. But times a negative huge. And so it's clear that this function goes to negative infinity. And okay, you could rephrase that statement in terms of limits. The limit of this function as x approaches negative infinity is negative infinity. I don't know why I wrote it that way, same thing. Okay, so limits, places where the function's undefined, roots, that seems like all the pre-calculus I could have done. Now let's do some calculus. Okay, so let's take this function and write it in derivative-friendly form as x, well, sure, x 4 minus x to the 1/2. And now we differentiate. So we take the derivative, and it's the root of the first, times the second, so times 4 minus x to the 1/2. We have done problems like this before now, and I think the past 2 weeks in a row we've done problems like this. So derivative of the first, what have I done? Sorry. Derivative of the first times the second plus the first times the derivative of 4 minus x to the 1/2. And what is that? It's going to be 1/2 4 minus x to the negative 1/2 back inside for the derivative of 4 minus x, which is negative 1. So now we need to, well, okay. Well, I'll write it one more time as 4 minus x to the 1/2 minus 1/2 x 4 minus x to the negative 1/2. But this is the form. This is the form in which, in my opinion, is most easy to work with when performing a subsequent differentiation. But it's certainly not the form which enables you to know when it's positive and negative, so we have to put in more work for that. Okay, let's go. We've learned how to do this. We need to factor out 4 minus x to the negative 1/2. And I'm going to be fancy and take out a 1/2 at the same time, because that gets my fractions out of the way and leaves me with the whole numbers on the inside. So factoring out 4 minus x, 1/2 4 minus x to the negative 1/2. I'm left with then the 1/2. There needs to be a 2 here to cancel out that 1/2, and that needs to be 4 minus x to the 1. And then here this is going to be minus x. Okay, again, this algebra is pretty hard, but if you kind of go slowly and carefully, and I think the most important thing is to double check what you've done by multiplying it back through. And if you do that, then you will see that we have done it correctly. Okay, what's left here on the inside now? This is 8 minus 2x minus another x. I think I've done this very problem before. So this inside here is in fact 8 minus 3x. And so the final form for which I will write my first derivative is it's 8 minus 3x. Okay, but I actually want to write that as negative 3 x minus 8/3, which is what it is after all, over 2 root 4 minus x. And I'm going to put a blue box around this so that I may analyze it. Okay, but now, and I gotta squeeze it into this space available here, I am going to differentiate again. So what's the second derivative? Writing very small, I am now reach back to, as I was saying, I will reach back to this version of the first derivative to perform my differentiation. Okay, so let's go. Oh man, this is not going to fit. Derivative of the first. What is the derivative of 4 minus x to the 1/2? It's 1/2 4 minus x to the negative 1/2 back inside negative 1. And now I am going to differentiate this second piece, for which I have to use the product rule. So it's the derivative of the first. I'm going to think of this negative 1/2 x as being the left function. So what is the derivative of negative 1/2 x? Is going to be negative 1/2 x. So derivative of the first times the second. So times 4 minus x to the negative 1/2 plus the, sorry, hold on, I messed up. Derivative of the first would just be negative 1/2. Derivative of negative 1 of x is negative 1. Derivative of the first times the second plus the first, which is negative 1/2 x times the derivative of the second, and the derivative of 4 minus x to the negative 1/2 is negative 1/2 4 minus x to the negative 3/2 back inside for the derivative of 4 minus x, which is negative 1. Look at this mess. Okay, let's go. What do we actually have here? We have a negative 1/2 4 minus x to the negative 1/2. We have another negative 1/2 4 minus x to the negative 1/2. And then we have all of that, which there are 3 negatives, which cancel, and we end up with negative x over 4 minus x to the negative 3/2. Okay, and so that's really negative 4 minus x to the negative 1/2 minus x over 4 minus x to the negative 3/2. Whew! Finally, we factor, according to this new advanced procedure. Let's see, we'll take out a negative 1/4 and a 4 minus x to the negative 3/2. And if we do that, we are left with 4 minus x to the 1 plus x. Cha-cha. And so I get, this can't be right, 16 minus 3x. That might be right in there. That's 16 minus 4, so 16 minus 3x. Okay. And so my actual final expression for the second derivative will be, well, that negative in the front makes this 3x minus 16. So this is really like 3x minus 16 thirds over 4 times 4 minus x to the 3/2. There are so many places where you could go wrong. I'm 80% convinced that I have done this problem correctly, but if I was doing it at home, I might go to like Wolfram Alpha and double check that. So I'm going to do right now x, which is maybe a little bit silly or something for me to not trust myself. Negative let's see, 8 minus 3x over good so far, and I'll do one more thing. Sorry. We'll double check this too. 3x, yeah, 3x minus 4. Okay, so I am experienced and relatively good at algebra, so I did all of this correctly. But, this is a bit of a slog. The real intellectual part of this is coming now, which is to use all of this information to graph the function. Okay, so just getting started really. Let's graph this function. We'll first do the thing that I said we would do earlier, which is to make a sign chart of the function itself. Now, it's not always possible to do that, but here it's possible because it's quite clear that this part is always the square root of anything is always positive. And so this right factor is always positive, so it's really the sign of x, which is going to determine the sign of the overall function. And so I say that this function changes sign from negative to positive at x equals 0. That's precalculus. But now we interpret our calculus, and so you have to be just very good at doing sign charts. And what do we see? Well, this is the form of the first derivative that we put so much effort into doing correctly and factoring and making all pretty, so that we can see, the denominator is always positive because the square root of anything is positive, so we can ignore the denominator. The numerator is just a linear function with a leading coefficient negative, which means it's like an upside down line, so it's going from positive to negative. Where? At 8/3. So at 8/3, a little bit less than 3, this function is going from positive to negative. And that means, based on the theorems from last week, if my derivative is positive, it means my function is increasing, and if my derivative is negative, it means my function is decreasing. Okay, and finally, the second derivative, which I add the number line for the second derivative directly beneath it, changes sign at 16/3. Anything to the 3/2 is guaranteed to be positive because, you're taking the square root of something is always going to be positive. So when you cube it, it's positive as well. You just have to know this, that anything to the 3/2 is positive. So the denominator can be ignored, and so on the top we have a line with positive leading coefficient, which means the end behavior goes from negative to positive. And where does it change? It changes at 16/3, which is like 5 1/3. But that's outside of our domain. And so, putting that all together, we see that for any number less than 4, which are the only numbers I'm allowed to plug into this function anyway, if you plug any number less than 4 to here, it's going to be negative. So that actually means that my second derivative is always negative. And that means, based on what we learned last week, that this function is guaranteed to be concave down. Okay, so much calculus, so much precalculus, sign charts for the function, the first derivative and the second derivative. Finally, we can graph this thing. And the graph is going to be a little bit underwhelming, perhaps. It's exactly the graph that you would have thought, man. If you plug in 4, what do you get? Answer, 0. So that I knew already. If you plug in 0, what do you get? 0. Those are my two roots. Furthermore, my function is negative until 0, positive thereafter. Okay. Also, as x goes to negative infinity, my function goes to negative infinity. Also, at x equals 8/3, 2 and 2/3, I'm going to have a relative max. I don't particularly feel like plugging that number into the function, but there's going to be a relative max there at x equals 8/3. And also this function's concave down always. So, what's it going to look like? Pretty much gonna look like that. And there it is. That's the whole function. It's going to be negative until 0, positive thereafter, and that's it. In fact, a very smart precalculus student could have probably graphed this function, basically, because you kind of know that locally near 4, it's going to look like the square root 4 minus x function. And what does square root 4 minus x look like? It's like x minus 4, but backwards. So like that. It's going to be half parabola with vertex at 4, 0, but facing left. And then x is just x, so near 0 it's going to be locally linear. So this is locally linear at 0, locally square rootish at 4, and the sign chart, which only requires precalculus, could have been used to determine that the shape is like this, and end behavior is also just precalculus. So what did we gain from doing all this calculus? Well, one thing we gained is that there's a relative max here at 8/3. That's not something we could have done. And also we now know for sure that this function is in fact concave down everywhere. Okay, 2 down, 3 to go. That took another 17 minutes, yeah. 3 to go. Twenty-three. 23. 3x to the 2/3 minus 2x. Okay, I think this one is perhaps not so hard. Yeah. Well, first of all, well, let's just begin. I can take anything to the 2/3 because I can take the cube root of anything, so there are no domain issues. End behavior, whatever. Never mind that right now. Let's just start. When is it 0? Maybe I do want to do that. When is this function 0? Okay, I could set this function equal to 0 and solve, but what's better to do is just the same old thing that we have been doing recently, factoring strange things, which is to take out as much as you can. And okay, I can obviously take a 3 out of these two terms, but they also share x, and so what we're going to do is we're going to take out the lowest power of x, which is x to the 2/3. I was going to do this later, but I guess we can just do it now. So 3x to the 2/3, if I take that out, I'm left with 1 minus, okay, well, x to the what times x to the 2/3 is x to the 1. Answer is 1/3. So actually, this function is, if you take a negative out here, this function is negative 3 x to the 2/3 cube root x minus 1. And this is the most, I think, useful form to have the function in when it comes to graphing and thinking about when it's positive and negative. So I'll do that later though. Now let's just take all the derivatives that we can and factor them nicely. So if I take the derivative, I'm going to go back to the original version because that's the one that's easiest to differentiate. So what's the derivative for x to the 2/3? Well,